Welcome to a special colloquium today. And we usually have, for your information, our conventional colloquium time is Thursday in the afternoon.
Okay.
And because you are special, we moved your talk to the morning because I think it's the best after everybody hears your talk, and then it's easier to start a conversation. So that was my suggestion. Anyway, so we have a special guest, Dr. Alexander von Hoegen. Did I get it right?
Almost.
Not close. Oh
no, it is close, but.
All right. So anyway, so here as our faculty candidate. Again, the committee has been very impressed about his background, training, and accomplishment so far. So Alex did his bachelor and master degree from Hoegen University, and then moved to University of Hamburg for a PhD. And I bet that his thesis work was conducted in Max Planck Institute for Structure and Dynamics of Matter. And then I guess it was largely due to COVID. After he received the PhD from in early 2021, he stayed a little bit longer at the Max Planck Institute for postdoc work, and then moved to MIT by late 2021 as a postdoc at there in a very productive group for the ultra fast spectroscopy, and this is how his expertise has been extended from early days working in X-ray based spectroscopy and then to the laser based spectroscopy. Did I get it right?
Yes.
And so Alex has been very active in a variety of senses, including research, of course, also kind of outreach activities. And so he received some recognitions about like oral presentation, and also MIT some kind of certificate.
Yes,
right?
yes.
And also, of course, other research fellowships as well. So again, we also have a very impressive publications. Up till today, he has at least like 18. And one impressive characteristic is during his graduate study, he made a first author Nature paper, right? And so this is something to our grad students. Okay, so that's the icon you needed to.
I'm sorry.
Look after that. So anyway, today he's going to talk about something about his expertise and something he feels excited about.
Yeah.
Right. There you go.
Yeah.
Alex.
Thank you for the introduction. Today I'm gonna talk about. So this is all work that I did during my postdoc. So and it's twofold. So one is using, as the title suggests, control. We want to do something. We want to control materials, and so for this we usually use THz light to manipulate layered quantum materials. And so this is one ingredient of the talk where we transiently change the properties of a material. However, there's then the other aspect of this work where now you have THz light and it needs to couple to your material, right? So that's the second part of this talk where I want to look into how can we shape and control THz Light-Matter Coupling. So how can we couple these terahertz photons into our material, and how can we control it? And so I want to start off with something that's pretty simple, is just a simple adiabatic phase transition. So where we, at a high temperature, which is temperature-driven, where at high temperatures above DC you have a pretty boring free energy surface, and then once you cool down your material, lower the temperature, and below critical temperature, your material stops developing all of these additional minima. Each of these minima corresponds to a different macroscopic property of this material. However, in thermodynamic equilibrium, your system will always end up in the lowest energy minimum. This is dictated by the thermodynamics. And so all of these adjacent minima, which all have unique properties potentially, are inaccessible to you. So, and what people have done in the past is to access these minima, they have used ultra-fast laser pulses. So usually in the near-infrared visible and UV light, where they quench the low energy physics, where they quench the low energy ground state, so that and promote the system into something that resembles the high temperature ground state, and then potentially also exciting these Coulomb oscillations. And then during the relaxation of this material, it can actually end up into one of these adjacent minima, which is long after the laser excitation. This is usually usually how people would drive these ultra-fast phase transitions into one of these hidden states. However, since we are now relying on this relaxation process, over which we don't really have a lot of control, this is pretty undeterministic. And a more deterministic approach actually relies on so-called strongly correlated materials, where you have strong correlations and strong coupling between the structural degrees of freedom, so the lattice, electronic degrees of freedom, so electronic hopping and the on-site Coulomb repulsion, and also spin ordering, so spin interactions. And all of these are strongly coupled to one another, and this then leads to the fact that the free energy is now not only spanned along one coordinate, but along, in this cartoon, along two coordinates. And this actually allows you to find favorable pathways around these energy barriers, which you can take to actually, while preserving this low energy ground state, to actually go into these hidden states. And so this is typically done by using low energy light to couple to the fundamental collective excitations of these materials to drive them to large vibrational oscillations, which is shown in this cartoon here, which then allows the system to actually dynamically bypass these potential energy barriers and then end up in one of these hidden states. And so this has been successfully done in the past, where people mostly use low energy light in the terahertz or mid-infrared region to collectively excite and coherently excite phonons in these materials. And this is usually dubbed nonlinear phononics. And so these types of experiments usually can be cast into like in three steps. So you need to be able to excite these collective modes, which is usually done with terahertz light. You need to be able to probe them ultra fast, so they have to have optical features that are characteristic of a certain state. And then this can be done then with different types of optics behind the experiment. And then also your material needs to have this sort of coupling. So, and this is then again twofold. You have the intrinsic coupling that I just talked about between these microscopic interaction parameters. However, the second one is the light-matter coupling. So you need to be able to couple your light to your materials, and this is actually something that we can control by shaping the size of the material. So basically, bringing it into a certain form will dramatically change this second aspect. And this is exactly the two parameters that I want to talk about. So in the first part of this talk, I want to talk about an example of a structurally driven of a dynamical phase transition. In the second part of the talk, I want to emphasize on how we can control light-matter coupling in the terahertz region by bringing our sample in a specific shape, for example, how this is impacted. And so for this first part, the material that we choose is a so-called thiophosphate. So it's one of these layered magnets where you have these adjacent layers. And depending on the magnetic ion, which is shown here in these blue balls, which form these honeycomb lattices, depending on the specific choice of the magnetic ion, these materials will turn out into different types of magnetic configurations. Because the choice of this ion will control the different exchange interactions in the material, so first nearest neighbor, second nearest neighbor, and third nearest neighbor interaction, and also the interlayer coupling between these materials. And so, depending on this, we can actually realize a plethora of like different magnetic states. And so the material that I want to focus on today is iron phosphorus trisulfide, which is here in the so-called zigzag phase. And so the specific choice of this ion then results into this zigzag chains here, where you have ferromagnetic chains, which are basically antiferromagnetically coupled to adjacent chains. And then again, antiferromagnetically coupled to the next layer below. And what we can already say is that, so this is a theoretical prediction over here, that this material is pretty close to a phase boundary. So this is usually something that means that your different states, that the zigzag state, or for example then also the ferromagnetic states, are very close in energy, right? So that you just need to kind of nudge the sample and it will turn out to be a ferromagnet. This is at least the hope that we people in ultrafast physics usually have. And so what is also important in this material is that you have this strong anisotropy between out of plane and in plane directions, which then in turn leads to strong excitations in the terahertz region. So this is kind of number one. So this is for the light-matter coupling. We need excitations in the terahertz region that we can couple to actually control, to actually drive them to large amplitudes and control the ground state. And so what people have been done in this material is, due to this large anisotropy, you get actually very high frequency magnon modes, which is a spin precession mode of the spins in these materials, and which is shown here as this red line, which starts softening, so it's very stable at low temperatures, and then it starts softening towards the so-called Néel temperature, which is the transition temperature. And how people identified that this is a magnon is basically due to the Zeeman effect. If you apply a magnetic field, this mode starts splitting into two degenerate modes, which then basically show this X-type pattern here, and they start changing frequency. And so this is so they then compute people in the past have basically carried out these Raman-type measurements then under this magnetic field, which is shown here. So you can very nicely see the splitting of this magnon mode. And the very interesting thing is, if you go to much higher magnetic field, you start seeing these avoided crossings here. So this here, P3, that's a phonon. And what avoided crossing usually tells you is that two collective modes are strongly coupled to one another, which then, since you see an avoided crossing here between the magnon and the phonon, means that the spin and lattice degrees of freedom in this material are very, very strongly coupled, because this splitting is actually pretty large. And so this is basically oh yeah, please.
What's going on with the, looks like, is that the P2 and P3 at the very high fields?
It's also, it's basically the same thing. So you also start getting this avoided crossing now with this other mode. So, because now your magnon, so up here, P3 basically at very high magnetic fields is basically a phonon again, it's not hybridized. But then your magnon starts coupling to P2. And so now this starts hybridizing into this collective, into this hybrid mode, what people like to call magnon-phonon in this case. And so these modes are, so what I'm showing here is Raman scattering. These modes usually do not have infrared activity. However, they actually start appearing in infrared transmission, so as little dips in your infrared transmission. And this means that your magnon, which is infrared active, lends infrared activity to these modes. So they start becoming actually these new hybrid modes that people like to dub a magnon-phonon. And if you then write down this very simple Hamiltonian here, you basically get the spin is coupled to the lattice. So this is usually my terminology: spin and lattice means Q. And so this is actually so this is our first step to controlling this material for these experiments, right? So we have this type of intrinsic coupling to this material, like the strong coupling between spin and lattice, and this is something that we need. The next step is, can we probe these features? Can we probe the magnetic state in iron phosphorus trisulfide? And indeed we can. So how we found this out is we just send a laser pulse through and we analyze its polarization state, in this case with a half-wave plate, which allows us to measure the polarization rotation that our sample induces when our laser beam passes through it. And you can actually see that above the critical temperature of this material, there's no polarization rotation. However, then once it goes into its magnetic state, this material shows like a very, very strong polarization rotation, which is due to the anisotropy of this material due to these zigzag chains. And we can also then again probe this with a quarter wave plate, and by replacing our half wave plate with a quarter wave plate, we're not measuring the polarization rotation anymore, we're measuring the ellipticity. So this is another polarization property of your light. And also again here, you can see like this very stark contrast between above the critical temperature and below the critical temperature. So indeed, with these two characteristic features, we are able to probe the magnetic state in this material. And also what we see here is that in the ellipticity, for some specific reason, we see so-called critical fluctuations. So there is already an ellipticity signal above the critical temperature, which can be brought in accurate with the fact that this material is actually predicted to be very close to a ferromagnetic state, so that your system is already kind of fluctuating and you pick up these fluctuations in this ferromagnetic state with this type of measurement. And so this is ingredient number 2 that we need. So we can optically probe this material in its magnetic state. And number 3 is we need the excitation. This is something that I've helped pioneer in my old group, and this is also something that Nugetic's group started working on already before I came, but then I also jumped on board, where we use strong terahertz fields with field strength of the order of 1 megavolt per centimeter. So this is already like a pretty large fraction of interatomic fields. These are very, very large terahertz transients. And so this is a measurement down here. So this is our terahertz pulse on a time scale of time delay, and we measure the ellipticity, again similar to before. And if you take a Fourier transform of this, you get this spectrum over here. And this is basically the terahertz. This is our excitation spectrum. And if we now draw in the lines from these Raman measurements, we can actually find very good overlap between the phonons and our excitation spectrum. There's only one phonon mode that's outside our excitation spectrum. And we actually find that also the magnon is covered by our excitation spectrum. So we are able to excite these modes using our terahertz light. So now this actually is then ingredient number 3. So we are able to excite these modes with our terahertz light. They should show strong coupling to one another, and we can probe the response of the material with our laser pulses. And so just to jump right in, so this is one of the measurements done here. So this is one of our time-resolved measurements taken at 10 Kelvin, measuring the polarization rotation, the transient change to the polarization rotation. And as you can see here, so once our terahertz pulse arrives, we get this very strong peak, which is a terahertz Kerr effect, which is then at longer delays followed by these rapid oscillations. And if you take a Fourier transform of this, you actually end up with this. You get these very, very sharp peaks that live on the order of like hundreds of picoseconds. So they live for a very, very long time. This is why they are so narrow. And so if we probe the same dynamics using the quarter wave plate, we get something that's very, very similar. So we see the same peaks here. We get very strong oscillations here. So both of these features are able to measure the transient features of this material.
Can I ask a question?
Please, yeah.
How long do you have to measure after the pump signal in order to have those very narrow lines?
Good observation. So here I basically truncated. So I basically zoomed in on this region just after time 0, but we actually measured out to 150 picoseconds. So we basically measured for a pretty long time of these modes, and then we usually stop this delay scan at a point where we don't see these coherences anymore.
And that's every time you measure a certain delay, that's a separate experiment? Or?
That is basically a separate experiment, which takes about 30 milliseconds. So you just you sit on a point, you integrate for 30 milliseconds, then you go to the next one, integrate for 30 milliseconds, and you repeat this for a couple of times. So taking one of these curves from 0 to 150 picoseconds takes about 20 minutes. So it's actually not too bad. And then this is the signal to noise of basically then one of these scans. So it's already decently high. For this material, for other materials, you will actually need to integrate a little bit longer. Did that answer? Okay, perfect. And so we can now basically all of these dashed lines here show you the position where Raman measurements found modes in the system, and we actually find perfect agreement between these measurements. And also what we find here, this red mode is actually our magnon. So we can actually see coherent oscillations of this magnon mode, which actually shows us that we are sensitive to magnetization dynamics, because once your magnon is oscillating, it basically transiently creates and destroys a magnetization in the material. And so as we see that these two measurements, polarization rotation and ellipticity, are very similar, we actually, for now on, I want to focus on the polarization rotation, because the signal to noise is slightly better.
Sorry, that was based on the comparison with the Raman.
Exactly. So these dashed lines are comparison to static Raman measurements.
That's what I'm saying. Otherwise, how could you distinguish
Exactly. We in our experiment we can't. So we actually for this we heavily rely on complementary measurements in this case.
Well, you also can get a computation to figure out.
But then people ask, can't you do an experiment? So to actually get to know more about the nature of these modes, and if you also see these fingerprints of this hybridization between magnons and phonons, we now conducted more experiments at this low temperature. So for one, we conducted an excitation field dependence. So we basically changed the strength of our excitation. And so what you would expect for the magnon, because the magnon is excited by magnetic dipole coupling. So the magnetic field component of your terahertz field couples to the magnetic dipole and linearly excites it. So it's basically like this linear excitation. This is exactly what we find, that the height of this peak linearly changes with the excitation field. So this is very much in line with this type of linear excitation. For then we picked this mode here, which people have already seen before in these Raman measurements. It's just a phonon. It doesn't hybridize with the magnon, and therefore what people just call it a Raman phonon. And a Raman excitation is basically the square. It scales with the square of our electric field, which therefore should basically also just show an excitation field dependence that goes with the square of our excitation field, which is exactly also what we find for this phonon. However, then there's this other mode, what people call this magnon-phonon. And so this is now this hybrid particle, which is half magnon, half phonon. So how does that scale? And what we actually find is it scales, in the beginning it scales linearly, and then it starts saturating. And I will come back to this in a second, but this is basically the transition from the magnonic behavior, which is linear, over to a more phononic behavior where it turns into a quadratic field. And in this specific case, the sign of the linear channel and the quadratic channel are of opposite nature. So they're basically destructively differing. I will come back to this in a second, I promise. So this already shows us these are kind of the fingerprints of this hybridization, and we can pick them up in our measurement. And as shown here, so this is this magnon-phonon, which starts, in our case, already shows that they're already hybridized at zero field. So this is an intrinsic property of the material which is not activated due to the magnetic field. It's always there. And we can go one step further, and we can now analyze the symmetry of these modes. So we can do so-called coherent polarimetry of these collective modes by rotating the angle of our terahertz excitation with respect to the crystalline axis. So this is this angle phi here, which is then shown in this polar plot down here. So for the magnon, you get something that looks like a dipolar pattern, as we would kind of expect because we're linearly exciting it. And so it should follow a cosine behavior. For the Raman, we now basically, since it scales with e squared, we would expect the square of this dipolar pattern, which is exactly what we find. So here, both lobes in this direction have the same sign, whereas here it's positive and it's negative. So how would it look like for a hybridized mode? And this is actually what we get. So we get something that kind of is a little bit squished on one side and a little bit elongated on the other side. And this is actually due to this aforementioned interference between this positive lobe here gives us an elongated positive lobe here, or in that case, negative lobe. And so this negative lobe here deconstructively interferes with this positive lobe, and therefore it is a little bit suppressed. And so if we would carry out this excitation field dependence on this side, so we carried it out on this side where it's suppressed, where they're deconstructively interfering, if we would go do the same experiment on the other side, which we did, you actually see an upturn in the excitation field dependence. So this gives us confidence that we can very much pick up this hybridization of these modes and this spin-lattice coupling in our experiments. And so then we went again one step further, and like how does this coupling evolve as a function of temperature? And this is something you can see here. So the magnon starts softening, the phonon is basically constant, and this magnon-phonon mode also starts softening, this increased softening of the magnon-phonon indicates an increasingly strong coupling close to the transition temperature, which is around here at 118 Kelvin. And this is actually very interesting that around where this coupling is proposed to be stronger now, we see this very small upturn down here at very low frequencies. And if you now increase our time window, you will actually see that this small upturn is actually a pretty big upturn in the FFT, and you actually also get this quasi-static offset, which only appears very close to the transition temperature of this material. So this is actually was very exciting for us, because that kind of means that this now stronger spin-lattice coupling close to the transition temperature actually leads to some sort of modification, long-lived modification of this magnetic ground state. So this was very exciting to see for us. And so if you take a full temperature dependence of this, you get something like this asymmetric shape. So it peaks at the transition temperature and then it's basically zero above. Where we got a little bit discouraged then is that also other people saw this. And they saw it not using terahertz excitation, but they saw it with optical excitation. So they're basically quenching the ground state, which is basically translates into a temperature increase. And so what we wanted to do is we want to do non-thermal engineering of this material, but this seems to be like a very thermal process. And so what this basically does is your laser pulse gives you a very small increase of temperature, delta T. But this then, if you basically follow this equilibrium curve of the polarization rotation, also translates into a very small change of the polarization rotation. So what you would actually be doing in your transient experiment is to actually sample the derivative of this curve if it were a thermal effect. And that's totally what we did. So what we found is actually that if you integrate this as temperature, you'll actually get like perfect agreement between the static measurements. And this was very disencouraging, because we thought, okay, we're actually doing something non-thermal here with our terahertz excitation. But it also seems like it's just increasing the temperature. What was a little bit more encouraging is that if you now replace your half wave plate with a quarter wave plate, so instead of measuring the polarization rotation, you measure the ellipticity, the temperature dependence looks dramatically different. So instead of this asymmetric shape, we now get this divergent shape, which is more or less symmetric around the critical temperature. And if you compare this now to the static ellipticity measurement, so you do this temperature integrated temperature integral here, you get something that's very different. So that already hints to us that there are non-thermal dynamics in the ellipticity measurements, and that what we capture with the polarization rotation is purely thermal dynamics in this long-lived state. And this is why I now want to focus on the ellipticity measurements and ask the question, okay, what is the cause of ellipticity in one of these optical experiments? And so for one, it's linear birefringence, right? If your refractive index along one crystal axis is different to the other one, your light basically starts turning elliptical if you come in. However, another aspect that can give you ellipticity is circular dichroism if you come in with linearly polarized light. However, in FPS, the circular dichroism, since it's a fully compensated antiferromagnet, should be perfectly zero. So you do not have a static circular dichroism. And this is also something that we measured and confirmed, that there is no circular dichroism in this material, as you would expect for an antiferromagnet. However, what we then turn out to do is actually to send in circularly polarized light left and right, and look at the transient change of the transmission of left and right circular polarized light, which is the definition of circular dichroism. And so this is what we found. So if you send in left circular polarized light, you get a small change, and basically not a long-lived change. However, if you send in right-hand circular polarized light, after the terahertz excitation hits here, you actually start seeing a dramatic change in the transmission. And if you now map the temperature dependence of the circular dichroism, which is unfortunately much noisier measurement compared to our polarization rotation measurement or ellipticity measurement, we actually find a very similar temperature dependence compared to the ellipticity measurement, which strongly suggests that the ellipticity change in this material and the circular dichroism come from the same physical effect. And so one thing that can give you a circular dichroism in your material, you need to break time reversal symmetry. And one thing that can do this is a magnetization, an out-of-plane magnetization. So this is basically very similar to what people usually do in a measurement where you have on a ferromagnet in this case, or on a ferrimagnet. And so this strongly suggests that the ellipticity and the circular dichroism come from a transiently induced, long-lived magnetization in this otherwise fully compensated antiferromagnet. And so we can fit this, and we find a very nice. So with this power law behavior, we find a very nice critical exponent, which is compatible with one of the critical groups proposed in this material. So a 3D icing model. And then what we can also do is we can start looking at the rise time dynamics of this material, right? Like how long does it take to establish the state? And we also find a critical divergence, again, with this critical exponent, which also is compatible with a 3D icing model. And this critical divergence in this, since this is a So
you have a very short excitation pulse, right? And then you wait 50 picoseconds.
Yes.
Why does it rise?
So if you go away from this, it rises much faster. So basically, it's like an impulse, and so I will talk about this very much in the end, where we talk about the theoretical understanding that we have. But what we find is that you displace a phonon mode, and this phonon mode is strongly coupled to the magnetization, and it creates a magnetization. And this is kind of a runaway effect, because the magnetization then leads to another distortion of the mode. So this is kind of self-amplifying in this case. And the timescales are dictated in this case by the timescales of the antiferromagnetic order parameter, which shows a critical slowing down, or like a divergence in their timescales close to the critical temperature. So the timescales are dictated by the antiferromagnetic order parameter in this case. So it's very much compatible with the second order phase transition, where close to the phase transition you have like softening of modes, and therefore the critical slowing down, because your energy differences between the initial, like the excited state and the initial state, are so small, so the driving forces are very, very weak. And yeah, so we find this divergence in the rise time. Now the question is, how long does it live? Because with our delay stage, so the delay between pump and probe, we're kind of limited to 150 picoseconds. We can't probe any further out. And it seems like it's still kind of rising after 150 picoseconds. But what we can do is we can look into before time zero. So, and this actually means if you see a before time zero signal as we do, is that your time, that these dynamics that you launched haven't had time to relax back to the initial state between two separate laser pulses, since this is a pulsed experiment where the pulses are separated by 1 millisecond. That means that our state that we're generating here, after 1 millisecond, has not yet relaxed back to its original ground state. And this is usually hints to heating, but we already know this is not heating in this case. And this is why we can now take this pre-time zero signal here and look at its temperature dependence to characterize the decay time of this photoinduced state. And again, here we actually find that this pre-time zero signal, which we trace here with these dots, also diverges close to the critical temperature. So this also means that the relaxation time of this new magnetic state, basically, which we can then in turn also take from this, because we have this formula, so we know the interpulse separation, which is 1 millisecond, and from taking this formula and working it out on this pre-time zero offset, we can actually then reconstruct the decay time, which we find here at 118 Kelvin to be 2.5 milliseconds. Yes?
So initially, your electricity goes up, it's positive, it grows, and then you're stating that after 1 millisecond, it's negative. And then you fit it with an exponent.
Yes, it's it is an artifact on how we measure it, because what we do is we always so what we actually do, we chop our pump. So what we do is we do a reference measurement between pump on and pump off. And so these two pulses are separated by 1 millisecond, right? But if your signal now has not had time to basically decay back between pump on and pump off, you basically reference your pump on measurement to something that is still photo excited. And if that has a positive offset, what you will actually get is basically you're referencing it to something that is larger than it should be. And so this gives you then this negative pre-time zero signal. It is not intuitive, but this is something that is due to, if you will, like an artifact in the measurements, that you basically get this cross between positive and negative. What we could do is we could just shift it up, and then this would basically give you then the correct time, but then would diminish the information about the pre-time zero signal. But
and this pre-time zero effect is stronger at higher temperature?
It is, yeah. So it diverges here at the critical temperature. So this is 118 Kelvin. So you can actually see it is pretty sizable at this. And then above the critical temperature, it completely disappears again. Yeah, please.
Can you really just move it up, because the signal is not just a constant shift. There's ringing.
Yes. So you cannot necessarily just move it up. So you would basically need to work out these things. So this is also a very simplified expression, because of course this pre-time zero signal is the cumulative effect of multiple laser pulses. So for this reconstruction, we took this into account. But just to make it a little bit simpler, I'm just stating this equation. But it is actually a cumulative effect, since it lives for 2.5 milliseconds, right? It's not only the next pulse, but it's actually also the one pulse over. So what we did actually is to purposely change the repetition rate of our laser to basically, instead of pumping every millisecond, we now, or rather every 2 milliseconds, we now pump every 5 milliseconds. We changed the chopping scheme and observed a very similar effect, which led us also to like a very similar expression for the decay time. Yeah, but those are like all these details that I try not to burden people with. But yeah, thanks for pointing that out. So this gives us now two ingredients that we can put together. So we observe a millisecond lifetime, and we get this circular dichroism, which now basically tells us that we're creating a metastable magnetization in this antiferromagnet that lives for a very long time. And so to make sense of this, we collaborated with a group of Anko Rubio in Hamburg. And so what they initially did is they calculated the low energy phonons to now make sense of this. Where does this state come from? And so they calculated the low energy phonons, and what you'll find, so these are the phonons in the relative spectral range. So here this means out of plane, in plane, and the arrows basically indicate in which direction these atoms are moving. And what you can see here is one of, in this specific case, which is the mode that people have identified as the magnon-phonon, we actually see that one of these chains is kind of more buckled, and this one is a little bit straighter. And whereas here, the chains are basically staying the same, but they're just being moved closer together. And so what they then added is this nonlinear coupling, this phenomenological coarse-grained coupling term, where the exchange interactions are now linearly modified by our phonons. So where all of these now, like ij, just mean these are different phonons. Yes?
And you said to start with, all of those phonons are only Raman active?
Yes, they're all Raman active. Exactly, yeah. And
So these modes are all in plane, right? Your application of magnetic field is perpendicular to AB plane, right?
yes.
So they are more sensitive to in-plane activities?
Yes. So the different colors here. Sorry, I haven't pointed that out. Thanks for reminding me. These colors mean those are spin up and spin down. So the spins on these atoms, they're all pointing out of plane. That's something. I forgot to mention that. So all of these spins are pointing out of plane. So in that sense, at least to my naive understanding, it would make sense that the magnetization also would point out of plane if you start modifying these spins and these exchange interactions. And yeah, so if you now include this into this, like if you now couple the lattice and the spin Hamiltonian, what you'll find is that these different modes, depending on the thickness of these lines, means if an exchange interaction is enhanced or weakened. What we'll find is that this mode that corresponds to the magnon-phonon, the exchange interactions on one of the chains is weakened, and on the other one it's strengthened. Whereas here only the exchange interactions between the chains is modulated, and here we get something that's called a columnar order parameter, which will also not give rise to magnetization. What they then found is, after coarse graining all of these couplings, is that the only phonon that can actually give rise to a magnetization, a finite magnetization in the system, is, lucky for us, is the magnon-phonon in this case. And so we get a coupling term of the shape like this. Q is the phonon, L is the antiferromagnetic order parameter, and M is the magnetization. And so we go 1 over, and so now we cast all of this into this effective Ginzburg-Landau model, where we couple now with this additional term. And what this gives rise to is that at a finite displacement of these phonons, you actually start creating finite magnetization minima here. So basically shifting these minima away from zero magnetization into a finite magnetization. And so you can actually solve all of this self-consistently. And this is exactly what I mentioned before, that once you displace the phonon, you create a magnetization, but this magnetization then in turn would displace the phonon. So it's a self-amplifying process. So it's a rather self-stabilizing process. And so in the end, the magnetization only depends on the antiferromagnetic order parameter in the system, and also it depends on it L squared. And L squared, close to the transition temperature, is basically the fluctuations of this order parameter, which at the transition temperature diverge.
Can you remind what's L in that?
L is the antiferromagnetic order parameter. So it's basically if you take the two sublattices and add them up, and or like add them up with a minus in between. And M is just the magnetization, where you basically just look at the overall magnetization of these two of the system. So how much are these two spins imbalanced, basically.
But in this approach, do they think about the individual spins as being just constants, or so? Like when you start,
yes,
and half of them is up and the other half is down,
yes,
then L is equal to 1.
Exactly. Yes.
And then what is the picture of when L is not equal to 1, when it's less than 1?
So they assume that the spins is 1/2, right? Or like a macroscopic, like an integer number. However, these are basically the macroscopic constants, which can then deviate from the integer value, at least in my understanding.
Yeah, so how is L defined in your case?
It is, it's basically, so you take the sum of all of these spins down and spins up, and you take the minus in between. So this is kind of the antiferromagnetic order parameter in this case.
So that just flips which layers are up and which layers are down?
Come again?
So negative L just involves flipping which layers are up and which layers are down?
Exactly. Yeah. It's basically a rigid shift across if you basically translate your exactly that. If you translate your unit cell one half up, you switch L from plus to minus.
Sorry, this is kind of a textbook.
Yeah.
It doesn't work that way as an order parameter for antiferromagnetic system.
Okay.
Anyway.
Yeah. And so the magnetization that we are generating depends only on L squared, which is basically proportional to the susceptibility of this antiferromagnet, which again diverges close to the transition temperature. And this is why we would actually expect something that scales as a square root of this magnetic susceptibility that you can see here. And so the critical exponent that we find is 0.65. And if you now divide the one that you find for the 3D IC model by 2, this is something that almost perfectly adds up. So
Okay,
this
it quite clearly does not only depend on L squared. It mostly depends on L squared.
Exactly. Close to the where actually L squared starts diverging. It mostly depends on this. So this is why we're not fully. I'm not fully married to all of these parameters,
Well,
but
I mean, if it's just a translation, then the bottom half of that figure should be completely redundant.
you mean this one, or
The one on the left.
this guy?
Should just be a just
That
be
is
180.
this is exactly so what this actually will do. So if you the thing is, we can only with this case we can basically only so the term of this coupling term, the sign of this coupling term is always preserved. So because as soon as you switch L, if you translate L one up, the lower half is redundant, as you said, because if you go from L to minus L, also the sign of Q will change, right? Because also the Raman mode will follow this translation, and so therefore the sign of Q will also change. So M is always positive. So you're fully right. The bottom half here of this figure is redundant in this case. Yes. Fully right. Yeah. And so this then basically brings us to this, where just kind of a summary of the results of this experiment, where we use terahertz excitation on this antiferromagnetic insulator, and we create a metastable magnetization. And so all of what I've shown so far is doing these experiments on 3D materials. And so so this was still a bulk material. This was still macroscopically thick, like micrometers. So it's very far away from the two-dimensional limit. So what people are now trying to do is actually to engineer these phase transitions also in two-dimensional systems, where they use terahertz light to go to the two-dimensional limit and actually start probing similar dynamics. However, here we have like a few roadblocks. So like very low light-matter coupling, because now you're atomically thin along one direction. And on the other hand, also usually these two-dimensional systems are very much confined to micrometer length scales. And in these micrometer length scales, your light-matter coupling dramatically changes. So your terahertz couples differently to a macroscopic sample than it will couple to a microscopic sample. And this is exactly what I now want to talk about in part 2 of this talk. And so so this is the current frontier, where people want to do these types of dynamical phase transitions in two-dimensional materials. And so the question is, what type of what is so interesting about these terahertz collective modes in these materials? So like, why is terahertz light-matter coupling so important? And it is so important because all of your collective excitations, or a large number of your collective excitations, happens at terahertz frequencies and at milli-eV energy. So for example, as I've shown you, phonons and magnons for one. On the other hand, you also have a lot of energy gaps in these materials that are in the milli-eV, so very, very small energy gaps. And on top of that, most of the electronic dynamics in these materials also evolve on terahertz timescales and at milli-electron volt energies. And where this becomes even more dramatic is if you start now taking, instead of one material, you start going to heterostructures of these materials, what people like to call Moray engineering, where actually now the kinetic energy of your electrons is being quenched due to deconstructive interference in these Moray lattices, and you start generating these flat bands. And these flat bands then host electrons with kinetic energies of milli-electron volts. So now all of your degrees of freedom in your system start becoming on the order of milli-electron volts and start becoming correlated. And so this is why I want to take all of this as a motivation that engineering and looking into terahertz light-matter coupling in these materials is extremely important. And so, just give you a little rebrief. Like this is typically how we do terahertz spectroscopy. So in macroscopic samples, this is very easy. You take your terahertz light field, you focus it down. You cannot focus terahertz light smaller than its diffraction limit, and this is determined by its wavelength. So the smallest terahertz spot that you can generate is half its wavelength, because otherwise your terahertz wavelength is ill-defined. And so for millimeter-sized samples, this is not a problem, because terahertz wavelength is usually on the order of 300 micrometers. So this fits very well. And so typically what you then measure is you send in a reference field, which you measure, and then you measure the transmitted sample through your field through your sample. And if something interesting happens, you will get an attenuation of your terahertz amplitude, and you will also additionally get these coherent oscillations, which usually hint at coherent dynamics in the system and collective modes. And so this is typically how people do terahertz spectroscopy. So now for small samples, how does the situation change? What happens now if your sample is much smaller than your diffraction limited spot? So this is a very, very exciting question. And actually what happens now is, in this situation, you basically have a constant magnetic electric field applied across, or like a homogeneous electric field applied across your sample if it's much smaller than the terahertz spot. And what actually happens now is that your boundary conditions and your boundaries of your sample become incredibly important, because you have to consider the current that is driven. For example, if you now apply an electric field and you displace your electrons, it has to be conserved and has to be zero at the boundaries, right? You can't like just take your electrons and take them out of your sample. So this is one boundary condition. And so what this will actually do is that you start driving your electrons across your sample. And so for one, it will lead to charge accumulation on the edges. So up here you get an excess of electrons, down here you get an excess of holes. Yes?
Sorry, I'll try to hear it. Can you go one slide back?
Yes.
And maybe one more, to the bulk sample.
Yeah.
So electric field is perpendicular to the propagation direction. So electric field is uniform along the vertical direction in this picture as well.
Yes.
But you said it's like very important that it's uniform versus non-uniform, but it looks like here it's also uniform.
It is also mostly uniform, but you still also on top of that you have like a Gaussian envelope on top of that. However, the main, you copy this. So the main difference is that now the edges of your sample are basically encompassed fully into your beam. So because here your edges are so far away from whatever's happening here, your sample, like your responses in the material, don't care about the geometry of the sample at all. So because it's also, since it is a Gaussian beam profile, it's like very smoothly defined in this case. But yeah, that is indeed the case. So the homogeneity of the field doesn't really matter that much. And so this is a situation that could arise now. If you start, for example, take this small slab of material, let's call it metal, you start displacing your electrons, and what will happen is you get a shape of the current that is terahertz induced in this material like this, where you have nodes on the sides and a maximum in the middle. And so also this charge accumulation here will actually now lead to an active restoring force of these otherwise freely flowing metallic charge carriers, which will actually now move your response from zero frequency up to a high frequency. So you go from a so-called Drude-like metal to something that resembles something more like bound charges or plasmons. What will also happen is that if you now start accelerating your electrons into the boundary, they will start getting reflected back. So we basically now start getting a current that moves the other way. And so what can actually now happen is that this incoming current that is propelled by your electric field and the reflected current can lead to actually standing wave patterns in your material, which basically give rise to counter-propagating currents with respect to your electric field. So up here, you have a current that moves this way, and down here in the lower half of the sample, you can actually have a current that goes the complete other way compared to your electric field direction. And so this actually exemplifies the importance of these boundaries, provided that your scattering time in these materials is large enough, right? So your reflected electronic wave needs to be able to propagate through the whole sample to actually give rise to effects that you also feel in the center of the material. Otherwise, if the scattering is too small, you'll only see those effects at the edges. And so conventional terahertz spectroscopy cannot measure these things, because you're averaging over this whole sample. And if you ever average over this current pattern, you won't get anything, right? Current up, current down, averages to 0. So you can't measure this with conventional terahertz spectroscopy. So how can we break the diffraction limit? Like, how can we see something that is smaller, than our beam size, or in this case? And so all of these approaches usually rely on taking your terahertz and bringing it to your sample. So what we want to do, or what we have done, is actually going the other way around. You take your sample and bring it to your terahertz, and basically bring it in direct contact with your terahertz source, where you can, and I will make a little bit more sense about this in a second. And so this whole approach that I want to present today relies on so-called terahertz spintronic emitters. These are incredibly small metallic sandwich layers of a ferromagnetic metal and a heavy metal like platinum on top of a common substrate. And these layers are 6 nanometers thick. They're incredibly thin. And if you excite these terahertz spintronic emitters, this is why they're called this way, locally with the pump pods, in this case it's a near-infrared laser beam, what will actually happen, you will launch a super diffusive spin current in these materials. So basically you start demagnetizing your ferromagnetic layer, this guy here, which we like to call Kofibi. And you launch a spin current, which then at the interface to the heavy metal, platinum, due to the inverse spin Hall effect, will turn, the spin current will get turned into a charged current, which propagates parallel to the surface. And so since this current evolves on sub-picosecond timescales, this will actually then lead to terahertz emission. So these are very, very compact terahertz sources. And of course, I cannot take any credit for this because these things have been around for a while. But these things now actually turning out to be incredibly useful for what we want to do. And so the idea now is to bring your sample, which is here Van der Waals material on a PDMS stem, to bring it to your material and basically deposit it on this terahertz source to basically make use of this pump pulse, which we can basically focus for our intents and purposes, can focus arbitrarily small. So we can create a terahertz source that's tiny, that's right next to our sample. The problem with this is, of course, you come in with a higher energy laser beam, you hit this, it excites a lot of terahertz, but also the residual beam that is being transmitted through the terahertz emitter will also photoexcite your sample. So this is basically, so what we would do, we would never be able to measure the equilibrium properties. How we solve this is we put in a so-called DBR, a dielectric Bragg reflector, which consists of titanium oxide and silicon oxide, so it's basically just glass. It's perfectly transparent for our terahertz, but it's highly reflective for our 800 nanometer pump beam. So the 800 nanometer gets perfectly reflected back with 99.8% efficiency, and the terahertz beam goes basically through without any problem. So this now allows us to do terahertz spectroscopy of these small samples basically on chip. This is what people like to call it. And so this is now kind of where we want to go in and want to start looking at these plasmonic modes. And so people have had other techniques to measure those with scanning tips and strip lines, where they actually found that if you launch these plasmonic modes, in this case it's graphene, they evolve on like micrometer length scales. However, our spot size here is about 10 micrometers. Yes, please.
So the blue is your now effective terahertz source.
So the terahertz source is here, and so the terahertz goes through this Bragg reflector, which is 2 micrometers thick. So it's, for all intents and purposes, it's still in contact with this source. And then this blue guy here.
The size of the blue part, this is smaller than the wavelength?
This is much smaller than the wavelength. So
it's sort of an emitter itself.
Yeah, so this guy, this is the emitter. This spans for like 5 millimeters, and the sample itself, let's go here, is about on the order of like tens of micrometers. So it's almost an order of magnitude smaller than the diffraction limit for our terahertz wavelength. So this is already, it's not where these people are measuring, because they have now pushed it to atomic resolution basically. But this is something that we we can't do it, but we also thought like there's an intermediate region of micrometer resolution, which is also very important to cover. And so, so we are looking now for a situation where we can get these plasmonic resonances that they found at graphene on micrometer length scales and much, much higher frequencies to actually bring it down to tens of micrometer wavelength and terahertz frequencies. And so for a typical metal, what we would expect in our experiment is we would expect a renormalization of the conductivity or of the currents at the edges. However, in the middle, it would still probably behave like a normal metal because the scattering is too large. We will not see the boundaries. So what we want to actually look at is a long wavelength plasmonic excitation in these materials, as I've shown before, where you have like currents going one way in one half of the sample and going the other way in the other half of the sample, which evolve on more on the order of like 10 to 100 micrometers. This is something that we can actually measure with this type of concept. And so we actually need to go now from a metal to a superconductor. So because especially in the superconducting phase, you start creating a coherent ground state of the superconductor, which basically it doesn't scatter. So you can basically now hopefully excite coherence motions of this now scattering, suppressed scattering ground state to create these plasmonic resonance. And for this, so we worked with a group of Philip Kim at Harvard. They made us a BISCO sample. So I'm only going to say it once. It's bismuth, strontium, calcium, copper oxide. So I'm going to call it BISCO from now on. And so they put this very small sample. So this is our scale bar here. So it's in this direction, it's about 45 micrometers. This direction, it's about 40. And the diagonal is about 60 micrometers. 20 nanometers thick. So it's 20 unit cells thick. So it's incredibly thin. And they encapsulated this with hexagonal boron nitride to protect it from air, because otherwise these samples start degrading very, very fast. And so this is a superconductor with a very high TC. So you can see the TC of this material is 87 Kelvin. And so what we designed an experiment as shown here, where we have now, of course, part of the sample that's not covered by it, so this is down here, and then part of the sample that's covered by BISCO and HBN. And so what we can now do is we can do basically a conventional terahertz experiment where we basically take our reference field by going through just the HBN, because HBN is basically perfectly transparent for terahertz. We get our reference measurement, and we can now move our focus, so of our pump, into our sample, and we actually can measure now, do a terahertz transmission experiment through the sample. And then we can compare these two things. And so what you can immediately see is that on one, the amplitude of this is dramatically reduced because it's a superconductor. It's basically very good metal, so it should screen terahertz. But we will also see is these coherent oscillations, which already hint at something, that there's already something that has what people call a finite mass or finite restoring force, so some sort of plasmonic resonance. And so what we can then do is we can take the normalized FFT amplitudes of this, so we actually see like this strong suppression. We see these very sharp dips in here as well. And what we can then do is we can divide our sample curve by our reference curve, and which then gives us our frequency resolved transmission through the sample. And you can see you get like a very strong depression here at around 1.5 terahertz at 10 Kelvin. And so since we're doing a field resolved measurement, we get amplitude and phase. So also of the transmission of these FFTs, we also get amplitude and phase. And especially here in this depression, you suddenly get this perfect, almost perfect jump of pi of the phase of the transmitted terahertz light. So below the transmission, you have minus pi half phase with the driving field, and above you have a pi half phase difference with the driving field. So this is already very interesting that this depression here in the transmission is very, very, very important. And so what we can do now, so these are our direct measurement coefficients. So there's really nothing done with this. This was just algebraic transformation. What we can now do is we can take the so-called Tinkham equation, which is only valid for a very thin film. And since we are here in the regime of 20 to 30 nanometers, this is we can consider it to be a thin film. We can actually take this analytical expression, plug in our frequency-dependent transmission, and actually calculate the frequency-dependent conductivity of this material, the terahertz conductivity. And this is shown here. So what we'll find is in the real part of the conductivity, you get a very strong peak. So this is the Lorentzian. So that means it is a collective mode of this material. It's a very, very strong mode. And in the imaginary part, you get this very nice derivative line shape, which also it corresponds together. These are Kramers-Kronig related properties. However, we don't need, since we're measuring amplitude and phase, we get both of them at the same time. So we don't need to do any fancy transformations. And if we compare this now to the bulk response of a superconductor of BISCO, so these numbers here and these trends are based on real data, you get a very different response. So in BISCO, you would expect in the imaginary part of the conductivity, you would expect in 1/omega divergence. What we get is we get a derivative line shape at finite frequency. In the real part, you would actually expect some sort of, like, this is residual scattering due to uncondensed carriers, which also should happen at low frequencies. We again get a finite frequency peak. So it's already very different to the light-matter coupling in a macroscopic sample. And this is already like the first demonstration that we can actually, that the confined electrodynamics are very different of these samples. Yes? Oh, okay. Yeah, and then of course we can do a scattering for temperature dependence of all of this. And what we actually find if we go from below to above, we actually find a stark contrast between below TC to above TC. So we actually lose all of these confinement effects. And if you now take the full temperature dependence of the imaginary conductivity, you actually find this very nice transition perfectly at TC. So you actually go from a geometry-dominated regime to a scattering-dominated regime. And so we can follow all of this. And so now the question is, can we visualize this? Is this possible? And of course, we can now just start scanning our excitation beam across the sample and basically do all of these experiments in a raster scanning pattern. And this is our image. So picked here 2.5 terahertz. So you actually see, like, it looks pretty similar to what we actually see in our optical microscopy image. And this is now a terahertz image. And each of these pixels has full spectroscopic information. So we can now go from 2.5 terahertz to 1.5 terahertz, where we see this resonance. We can start seeing these patterns inside to extremely low frequency of 0.5 terahertz, and where it looks dramatically different. So you can actually see that this confinement changes the frequency-dependent properties of this material dramatically. And we can compare this again to about 110 Kelvin, where you see it dramatically changes. So especially these fine structures that you see here inside the sample, at 110 Kelvin, completely gone. It's basically a homogeneous excitation. And so now we can do the same trick. We can take the Tinkham equation and convert every pixel into conductivity. And this is what we did here. So this is above TC, so you see an almost homogeneous response inside the sample. Whereas if you go below TC, you actually get, at 1.5 Kelvin, 1.5 terahertz, you actually get this perfect flip between positive to negative, which is what we would expect from like a fully expanded plasmonic resonance in this material. And which this is now shown here as a line cut. So if you take a line cut here along the diagonal, you get something here that only shows something at the edges, as we would expect. Also note here that this is like a very, very different color scale. And here you actually get this very, very nice sinusoidal pattern. And if you compare it to this example here, it makes sense. This is a plasmonic resonance. And now we can, of course, now take its wavelength and take its momentum. And what we can do, and this is the last thing, is we can now, to actually make sure that the currents in these two areas, blue and red, go into different directions, we can actually look at the electric field that is emitted from here and emitted from here. So this is spot 1, which is in the blue region, spot 2 in the red region. And so the current should be directly proportional to the electric field. And what we actually find is, of course, we find these nice sinusoidal patterns, which are a fingerprint of our plasmon. However, if you now overlap them, you actually find an almost perfectly pi out of phase between these two emitted electric fields, which should be proportional to our current, which shows that in these regions, the currents are actually going into different directions. And so this was, in that case, a very nice demonstration of this plasmonic resonance in BISCO. This is still very much work in progress. So we're right now working with theorists to actually see, is this indeed a Cooper pair plasmon? Is this due to the condensed carriers, or is it still due to lower scattering normal electrons in the superconducting phase? So these are still things we want to answer, but this is something we're very, very excited about. And so now I'm at my conclusion summary. So this is something I hope I can convince you of, that we can actually now do terahertz hyperspectral imaging with subdiffraction resolution of these terahertz properties. And then in the first part is that this now opens new doors for this light matter control of small samples, because now actually we have a handle on how to measure this light matter coupling. And the question is, what's next, right? Like, what can we do? And of course I could say, we're just going to measure every small material out there. But that, I feel, especially with the story of this talk, this would be like a little bit unfair. I think what I'd rather want to do is like actually now start exploring like micrometer scale plasmonic resonances in artificial lattices. You could, for example, take this Kagoma lattice and drive plasmons through it, and in hopes to realizing some sort of like a plasmonic band structure, for example. Like this would be very interesting to actually start studying like these types of properties, but like more on a micrometer scale, more on a practical scale in the terahertz regime. The other one, straightforward, is cavity electrodynamics, right? You basically now you can take one of these terahertz cavities, and you can actually start visualizing them. This is actually like an image that we did, and we found actually this very nice field enhancement where you would expect it if you apply an electric field in the horizontal direction. So that you can start mapping these plasmonic resonances in cavities. And this now gives you an open door for cavity quantum materials. So you can actually take one of these tiny 2D materials and put them on one of these plasmonic resonators, and you can actually start doing now like cavity electrodynamics with these materials. This is something very exciting. And this there's a lot of like theoretical work which then proposes that this allows you, if the light-matter coupling is strong enough, actually to in steady state change the material properties. And the last one is instead of relying on these plasmonic cavities, you actually start shaping your materials themselves. So you make your material the cavity, because especially now with like nano patterning techniques, this should be possible to actually. It's probably not this structure, but you can pattern one of these materials into one of these resonator structures in hopes to actually enhance its light-matter coupling. And then, last but not least, combining it with the first part of my talk, you can do all of these things time resolved. You can basically now locally perturb these materials with a strong driving, and you can actually then start changing these light-matter coupling parameters in time. And I think with this, I want to thank everyone who was involved in this group, and especially thank you for your attention.
All right. Questions, comments? You have already took a lot of questions. So
I actually have a technical question.
Yeah.
For you. So for this spin-lattice terahertz emitter, what is the conversion efficiency? It's pretty low.
It's very low, but also it is not as low as you think. So if you take one of these things 6 nanometers thick, if you send the same amount into a 1 millimeter zinc telluride crystal, you get the same conversion efficiency. And so the conversion efficiency is on the order of like 10 to the minus 6, 10 to the minus 5 in power, not in field. But also in zinc telluride, it is actually not that much bigger. They are definitely completely outperformed by any type of organic nonlinear crystal.
So is there any near field effect? Because you're still assuming there's an oscillating field.
There is. This is also one of the reasons why we see these plasmonic features, because your field still kind of explores the whole sample, but you get a local measurement of a non-local response of your material, right? Okay. And so if you really would just like only be locally probing, you wouldn't see these things, right? You really need something that is kind of evolving outwards a little bit. So we have done some finite element simulations. And you can still, in this regime, you can still kind of assume that you're having like a small Gaussian spot that has basically just a field component in this direction. And then, of course, it starts coming out into a spherical wave, and then things become a little bit more complicated.
I know you tried to stay out of these technical details. In the pump probe measurement, usually pump probe measurements, which since you have to average multiple pulses, you have to know that the system is back in a well-defined state before you hit it again.
Yes.
And this pre-measurement suggests that pre-state is different for all of those different temperatures.
Exactly.
So obviously you had to find out that it was however 4 whatever it was,
yes,
the real length, but then how do you decide that those pre-measurements are well enough control? I guess maybe it's just the first pulse, you throw that away and then keep the rest?
It kind of is. So we actually changed the repetition rate, like the duty cycle basically of our pump. So instead of having one pump every millisecond, we actually put it to every 5 milliseconds. And then after 5 milliseconds, you would actually see this pre-time zero signal is basically completely gone. But it's actually pretty nice because by kind of then referencing to like 1 millisecond, 2, 3, 4 milliseconds, you can actually see how the size of this pre-time zero signal starts changing. So this gave us a handle on this and also made us confident that this hand-waving analysis of this pre-time zero signal is actually accurate.
So I have a question for the first case about the antiferromagnetic transition.
Yeah.
And so you were talking about your dynamic probe overlaps with the static probe, right? In terms of transition period.
Yes.
So I was really curious because I would assume there is some dynamic response in this transition period, even it is a second order phase transition.
Mm-hmm.
Have you ever done heuristic
We
check?
we did not. We did not. Also,
I really think
yeah.
this is a cool thing to check.
It's we definitely thought about this. I think one of the reasons why we didn't do it, because also the theorists told us it is it would not really since it is actually not a ferromagnetic state that we are generating. It's more like a ferrimagnetic state, and also you're kind of just changing the fluctuations of one chain with respect to the other.
Yes, this is exactly the reason I'm asking.
Yeah, I think it would be so. Hysteresis, you mean like a temperature hysteresis, right?
Either
yeah.
temperature or field.
Yeah. So
basically, you will have a powerful probe.
Yeah.
You could be probing the differences
Yeah.
somehow.
So what we've tried to do, and that unfortunately was not fully successful, is to do Hall effect measurements of this. Mm-hmm. So where basically we take a small sample, we put it on a Hall bar structure, and we apply our pump, because since it lives for milliseconds, you can actually start doing these electric measurements. Right. Due to difficulties, that was just very unconclusive. But yeah, it is just always, since you're repeating these measurements for so long, it is especially combining these measurements with the magnetic field is not trivial.
That's true.
Yeah.
All right. More questions?
I have one question regarding the hidden state in your first part. And can you comment if there's any structure change in this hidden state?
You mean crystal structure, or
like stacking fault or chiral domain formation, something like that?
I would say probably not. So this is actually an experiment that is underway right now, where they took this material and the same pumping conditions to the mega electron volt electron diffraction at SLAC. So they want to look at this and actually start looking at these structural features that you were talking about, whether you can see domains or forming or something similar. From these measurements, we can't say. From these hopefully new successful measurements, which are actually happening, I think, as we speak, we hope we can say some more. Yeah.
All right. If there's no more question right now, but he's here today and tomorrow, I'm sure many of us have a chance to interact with him one way or the other. And let's thank Alex one more time.